In this video, we're going to review how to predict the shapes of molecules. The shapes of molecules are crucial in their chemistry, and so understanding their shapes and how their shapes arise is really important as well. So to understand the shape, we need to look at the pairs of electrons inside a molecule. So inside a molecule, you've got two types of pairs. You've got bonding pairs, which is where a covalent bond is occurring between two atoms where they're sharing electrons, and you've also got lone pairs, and that's where electrons are paired up because they like to be in pairs because of their opposite spins, but they're around the same atom, so they're not being shared, and those two things will govern the shape of the resulting molecule, because the repulsion that occurs between the pairs will actually force the molecule into certain shapes. So the theory we use to describe this is called valence shell electron pair repulsion, and sometimes called the VSEPR theory, and we can use this to explain what's going on. So if we look at these molecules here, I've got different numbers of bonding pairs. So for example, in beryllium chloride, I've got two bonding pairs, so that means that the dot diagram would look like this. And so if I was to draw the valence structure, it would look like this. However, you need to remember to add the lone pairs that the chlorine has. Now the chlorine doesn't actually do, the lone pairs on the chlorine don't do anything, but the lone pairs the bonding pairs inside this bond here repel each other, and so they force the molecule into this shape where there's a 180 degree distance between them, and so that actually angle between them, so that bond angle is the furthest apart that those two bonds can get. So it's the maximum angle you can get in that particular arrangement. If you suddenly introduce a new atom, so there's a three bonding pair situation here, you can see that they're going to spread themselves out only by 120 degrees, because 180 degrees is no longer possible. Once again, we need to remember to include the lone pairs on the fluorines here. Now these don't have any effect because they are also as far apart from each other as possible in this situation. Okay, and the bonding pairs in the middle here are repelling each other too. And that's called a trigonal planar structure because it's a triangular flat structure. Now when you have four bonding pairs, you suddenly have this three-dimensional structure form, where the best way of arranging the atoms is in two V shapes opposite, like perpendicular to each other. So the angle formed is 109.5, and this is true, the same angle everywhere between all of them. And this is the furthest apart that those bonds can get from each other, those bonding pairs. They call this a tetrahedron because there's four faces to it. So if I was to draw it as a three-dimensional shape, there are triangular faces, and there are four of them, equal triangular faces. So that's where tetra comes from. Five bonding pairs, you can see that we get an unusual structure where there's actually two different angles here. So the first three bonds are spread evenly around the equator here. These are called equatorial bonds, and they are 120 degrees from each other. Okay, but there's also an axis here, which these axial bonds are 90 degrees from the equator. Okay, so that's the most spread out we can get all of these bonds to be. You can see the dot diagram here does not show that structure. Okay, the three-dimensional structure is very different from the flat dot diagrams. They call this a trigonal bipyramidal because there's two pyramids stuck together. Okay, and they're triangular-based pyramids. Lastly, we've got six bonding pairs. So this forms what we call an octahedron, which is where there's 90 degrees between everything, and that is the furthest apart that those bonds can get from each other. Now all of these examples do not have lone pairs on the central atom. So when you have lone pairs on the central atom, it gives rise to a whole new set of structures. So if we go down now to look at some examples of that, if we look at when we have one lone pair and 3 bonding pairs, we end up with what we call a trigonal pyramidal. So an example of this would be NH3. Okay, so NH3 has 5 electrons around the middle there, and H is around the outside there, and so that's a complete octet for the nitrogen. And there's a lone pair here, and this lone pair forces by repulsion the bonds downwards. So instead of a tetrahedron, it looks like a tetrahedron, but because there's no atom here, it's actually only the bottom that we focus on, and this is a pyramid shape. So that's where the name trigonal pyramidal comes from for that one. So the lone pairs are acting in a repulsive way to the bonds there and forcing them down. And you can see here the other options you can get. So this is where you've got 2 bonding pairs and 1 lone pair, forming an angle there. You've got 1 lone pair and 4 bonding pairs. You've got 1 lone pair and 5 bonding pairs, causing what they call a square pyramid. So that's a square-based pyramid, which goes down the page like that, or you could go up the page as well, depending which way you drew it. And then we have substances where there's 2 lone pairs. So the most famous one is water. So water has a full octet there with 2 lone pairs, and we're going to learn about how to get these dot diagrams again in a moment, but you can see the lone pairs there and there, and so that means that the lone pairs act like these orbitals sticking out, and they repel the other bonds around, so the hydrogens end up at an angle to each other rather than being a linear molecule. And this is what gives rise to the V shape that we often depict water as. 2 lone pairs and 3 bonding pairs causes this T shape. So this is a 90-degree angle here, and the lone pairs sitting on the outside there form 120 degrees with the other atom. So an example of that is shown below. So you've got chlorine trifluoride. So if you have a Cl and okay, that forms a T shape. And then lastly, square planar. So that's where you have an octahedron, but instead of 2 atoms top and bottom, you have lone pairs. So this is where you have things like xenon tetrafluoride. So that's where you've got 4 things around the outside. And that causes this square flat structure. So that's the overview of the types of shapes you can get and why. The next step is learning about how to find those shapes given the formula. So let's look now at an example. CH4, methane. What we're going to do first of all is add up the valence electrons of the substance. So carbon has 4 valence electrons. Okay, so we're going to draw them now. Okay, and the hydrogen, I'm going to use a different colour now. Hydrogen has 1 valence electron. So now if I draw these, I'm going to put the most electronegative atom centrally, but if there's 2 elements only, just put the element that you have the fewest of. So in this case, that's the carbon that I have the fewest of. So I'm going to put the carbon in the middle, and I'm going to draw carbon's electrons on the outside here. So it's good if you can rub these out and arrange them as you need, but I'm just going to start by putting them there. Then I've got 4 hydrogens around the outside. Okay, and each of those has an electron that's going to bond. And the reason you want to bond these is to complete as many octets as possible. So, or as many shells as possible. So we can see here that hydrogens now have a full shell. And actually, if we count the electrons around carbon, also has a full shell. So now what we need to do is we need to just, having done that and filled the octets, we need to say how many electron pairs we have. So we have 4 bonding pairs. And we have 0 lone pairs. And that means that it's going to be a tetrahedron, a basic tetrahedron. If you go and look at the options there, let's get rid of these, we can see that we're looking at a basic structure of a tetrahedron there. Okay, 109.5 degrees bond. Now, if we look at the next example, we've got NH3. So once again, they've given us the formula. I'm going to write down the valence electrons for each. So this one has 5 valence electrons. So I'm going to draw now 1, 2, 3, 4, 5 because it's in group 15. And the hydrogen has just the 1. Okay, and so I'm going to put the most electronegative and the one that I have the fewest of as the central atom. So I'm going to put the N in the middle. And this is where you want to bond as many times as possible for the hydrogen. So I've got 3 hydrogens, so I'm going to just put all 3 of them around here now. Okay, and I'm going to put their electrons in a bond. And I'm going to put the bonds in there for the hydrogens. Okay, and then I'm going to count the nitrogens. I've got 2 left, so that's going to form a pair that's a lone pair. So now I've got to count them, and I've got 3 bonding pairs and 1 lone pair. And that means that I have a tetrahedron structure, base structure, because there's 4 total, but it's going to be different from the normal. So I'm going to go look at this table now. The tetrahedron column is here, where we've got 4, and it's going to be this one here with a lone pair. So this is a trigonal pyramidal structure. So when I draw this now, I'm going to draw the lone pair at the top, and I'm going to draw the 3D structure like this. Okay, and that shows the angle there would be based on the tetrahedral angle of 109.5. They actually do affect slightly. The lone pairs are not quite the same as a perfect tetrahedron, but we can go into that another time. So that's a quick overview of what you would do to work out the structures. The last example I'm going to do is water. Okay, so once again I've got oxygen with 6 valence electrons. I've got hydrogen with 1 valence electron. And so if I was to draw these, we've got them pairing up there. 1. Okay, now these will form a different structure to the last one. So I'm going to put the most electronegative in the one I have the fewest of in the middle, so oxygen. I'm then going to put the hydrogens around it. So hydrogen, hydrogen. Okay, now the hydrogen is going to bond if it can, and the oxygen is going to bond there. So that's 2 bonding pairs, and now I count around the oxygen. I've got 4 left, so I'm going to put them as lone pairs. So once again, that gives rise to a structure where it's based on a tetrahedron. I've got 2 bonding pairs this time, and 2 lone pairs. Okay, so that's an overview of how to find the structures and shapes using VSEPR theory. More advanced questions will look at when you have charges. So with the charge, you simply add or remove electrons from the total before you decide on how many lone pairs and bonding pairs you've got. I'm going to do a separate video for some examples of these. Alright, thanks for watching.